Welcome, future CPAs, to this explainer. Okay, today we're hacking a topic that honestly trips up way too many accountancy students on the MAS section of the board exams: sensitivity analysis and computer solutions. But we're going to do this differently. We're going to use pure logic and leave the messy math to the software so you can focus on being the strategic advisor. By the time we're done here, you're going to have a rock-solid mental framework built for long-term retention, literally designed to stick with you for the next 2 or 3 years until you actually sit for the LCPA. Here's our study guide roadmap for today. 1. The LECPA MAS mindset. 2. Decoding the shadow price. 3. The range of optimality. 4. The range of feasibility. 5. Reading Excel solver reports. And 6. The ultimate LECPA bullet review. Let's get into it. Section 1. The LECPA MAS mindset. Listen, to really conquer this topic, you've got to completely shift your perspective right now. You're no longer just a college student crunching numbers on a calculator. You're a high-level business advisor dealing with real-world what-if scenarios. Remember, linear programming software like Excel Solver does all the heavy lifting for you. The board examiners, they don't care if you can do complex simplex algorithms by hand. They want to know if you can look at a computer output and actually advise management on what happens when things change. Like, what if materials get way more expensive? What if we magically get 10 more hours of labor? The software computes, sure, but you decode.
Section 2. Decoding the shadow price.
Let's decode our first highly tested concept and see how this actually builds your advisory toolkit: the shadow price. Economists and textbooks sometimes call this the dual value. But honestly, rather than memorizing some dense textbook formula, I want you to think about this purely conceptually. It's simply the absolute maximum premium your boss should be willing to pay for exactly one additional unit of a scarce resource. So if the shadow price of assembly time is 50 cents, you march up to your manager and say, "Do not pay more than a 50-cent premium per hour for extra overtime, or we're literally losing money." It is that simple. All right, let's do a quick active recall prompt to stimulate those neural pathways. This helps so much with retention. Think about this for a second. If we already have excess capacity of a resource, which in technical terms is a non-binding constraint with Slack, would we logically pay extra cash to get even more of it? Zero. The answer is literally $0, because resources in surplus are considered free goods in economic terms, meaning their shadow price is always going to be zero. Think about it. If a machine is just sitting there idle for 10 hours a week, paying a premium to rent another machine makes absolutely zero business sense. So burn this into your memory right now. Surplus equals a zero shadow price.
Section 3. The range of optimality.
Moving on to the next crucial metric, let's look at the range of optimality. This is basically all about how much our per-unit profits can bounce around in the market before we have to totally tear up our plans and formulate a brand new production mix. This rule strictly applies to your objective function coefficients, which usually just means your unit profits. As long as the profit per unit stays inside this specific allowable range, our current production mix, say making 30 X-Pods and 40 blueberries, remains the absolute best choice. We don't have to change our factory output at all. But beware, because here comes a classic LECPA exam trap. I really want you to analyze this one carefully. If a unit profit changes, but it stays perfectly within that range of optimality, does your total overall profit stay exactly the same? Trap avoided. The correct answer is no, absolutely not. The combination or the mix of the products we're making won't change, but since the actual profit per unit just changed, our total bottom line profit is definitely going to recalculate, right? Like if you make $1 less per item and you're still making 40 items, your total profit drops by $40. The mix is the same, the money is different. Okay, to lock this in your brain for the next 3 years, we really need to visually compartmentalize it. Your brain loves visual structure. So on the left side of your mind, put the range of optimality. This deals exclusively with money and profits. And on the right side of your mind, put the range of feasibility. This deals exclusively with physical resources and constraints. Just keep those two sides separate and you'll never get tricked on a multiple choice question again. Section 4. The range of feasibility. So let's dive a bit deeper into that right side of our mental map. The range of feasibility tells us exactly how many extra hours of labor or kilos of raw materials we can add or subtract before that shadow price we decoded earlier just becomes completely useless. I mean, if we add too many hours of assembly time, eventually we're going to run out of some other material, right? The range of feasibility tells us the exact limits where our current shadow price actually holds true. Oh, and this brilliantly illustrates a funny little quirk you're going to see on computer outputs. If you ever see a massive scientific number like 1e plus 30 for the allowable increase of a non-binding constraint, do not panic.
It literally just represents infinity in Excel. It just means there's no upper limit to adding more of something you aren't even fully using yet. It's infinite. Section 5. Reading Excel Solver Reports. All right, time for a simulation. Let's look at exactly how this data is structured on the computer outputs you'll be staring at on exam day, stripped of all that distracting visual clutter. When you look at the variable cells section of a solver report, I want you to zone in entirely on just 3 columns: the objective coefficient, the allowable increase, and the allowable decrease. To instantly calculate your range of optimality for XPODs, just take that coefficient of 7, add the increase of 3, and subtract the decrease of 0.33. So boom, the range is 6.67 up to 10. Super simple, right? That is your money site. On the flip side, the constraints table is your resource side. This is exactly where you locate the shadow price. See it? It's 1.5 for electronic time. You get your range of feasibility by just applying those allowable limits to the right-hand side constraint value. 240 plus 60 gives us an upper limit of 300. 240 minus 40 gives us a lower limit of 200. And as long as our hours stay anywhere between 200 and 300, that $1.5 shadow price is perfectly valid. Section 6. Ultimate LACPA Bullet Review. Let's lock all this knowledge into long-term memory for some rapid multiple-choice recall under extreme exam pressure. Take a mental screenshot of the slide right now. I call this the 3-second rule. When you read a board question, you should be able to map it to one of these 5 bullets in 3 seconds flat. Shadow price is the max premium. Non-binding surplus means a 0 shadow price. Optimality is about profits. Feasibility is about physical resources, and staying within allowable limits means your shadow price is valid. If you can instantly recall these 5 bullet points, you're going to rapidly eliminate wrong choices and entirely dominate the MAS section. So let's actually apply this. We drop from 100 hours to 90. That is a decrease of 10. Does 10 fall within our allowable decrease of 20? Yes, it totally does. Because it's within the limit, our $1.50 shadow price is valid. Therefore, losing those 10 hours costs us 10 times 150. Total profit drops by 15 bucks. You apply the range of feasibility and you decode the bottom line like a pro. But I'm going to leave you with a final advisory challenge to chew on. What happens if multiple constraints change at the exact same time? Like if labor drops by 10 hours, but materials increase by 50 kilos, does your shadow price still hold true, or does the entire system just break? Think about how you'd advise management then, and I'll catch you in the next explainer.